All right, so we're taking a look at 6.4, which is a section I bypassed. I taught you a little bit of it to get you comfortable with something, which was writing inverses. And 6.4 as a teacher is something that I think is probably the hardest thing for most kids in the logarithm section to grasp, which is the graph of a logarithm. So I'm approaching a little different this year. Like I said, I switched some things around. The recap here is to find the inverse of something old, 3x squared minus 5, provided x is greater than or equal to 0. Now, the reason this exists right here is because if you graph 3x squared minus 5, you'd fall 5, which some of you know, and then this would be your graph. And this fails the horizontal line test. So it is not 1 to 1. And only 1 to 1 has an inverse. So when you say restricting so that x is greater than 0, you're basically throwing away part of the graph so that now it passes the horizontal line test. So there was 30 seconds of your life. Hope that made sense. Now, do you remember how to find an inverse? It's pretty simple. You swap your x and your y, and then you resolve for y. And then finally, you replace y with some sort of notation. Hey, Miss Patty.
I was gonna look it out. I'm gonna make an announcement that nobody.
Actually, I worked that out. I'll go down there.
Okay.
So I'll be able to go down there.
No, I'm talking about students in the teacher's lounge.
Oh, okay.
I'm going,
I thought we were talking about something else.
no, I'm gonna make an announcement that students are not allowed in the teacher's lounge.
All right. Sorry about the interruption. Miss Patty was telling me she was going to make an announcement because somebody stole a couple of my energy drinks out of the fridge. That's aggravating. I need this energy. Anyways, back to this. Replace y with the inverse of f of x. Let's see here. So first step here, we literally kind of get the f out because this is y and it becomes an x equals 3y squared minus 5. This one's easy peasy. We're just going to add 5 to both sides. And then we're going to counteract the understood multiplication with division. And that would be y squared. And there's a reason we don't include the plus or minus here. We don't include the plus or minus here because of this restriction. So if you're wondering why I don't use the plus or minus symbol here, it's just because I made that restriction. I'm only caring about the positive aspect. So anyways, this gives me y is the root of x plus 5 sitting pretty over 3. And then I use my notation. Where was I? Oh, yeah. Now, its inverse would be a square root. And instead of having 0, -5, it would have -5, 0. And then it would look like that. Anyways, those are cheap rough-hand graphs. All right, so what is a logarithm? A logarithm is the inverse of an exponential function. That is the actual definition of a logarithm. It is the inverse of an exponential. Font's kind of small, isn't it? Let me make that bigger because some of y'all be blind. I could probably make this thing like 40 and Arden still wouldn't be able to read it. But anyways, really small text there. Let's make it bigger. There we go. Inverse of an exponential. What do inverses swap? Inverses swap x and y, or you might say they swap something a little more mathematically inclined here, domain and range. Anything that's related to x gets swapped with anything that's related to y. So since x and y get swapped, if an exponential function has a horizontal asymptote at y equals 6, then the logarithm, if we swap x and y, would have something at x equals 6. So let's compare and contrast. We have something at y equals 6, and it was dashed because it was a horizontal asymptote, and now we became x equals 6. That's vertical, isn't it? So it has a vertical asymptote. Now, if you've forgotten what it means to be an asymptote, it generally means a line you don't cross. That's what it generally means. The horizontal asymptote is actually able to be crossed. The vertical is never able to be crossed. And when I talk about the horizontal asymptote being crossed, that's specific to certain functions. All right, graph f of x is 2 times 3 of the x and its inverse. The inverse of f of x being log base 3 of x over 2, and I think I did that right. So we're just going to need a table, right? This thing has no vertical or horizontal shifts, so the table is pretty easy. We can just start our table at 0 and then add 1. And this is for f of x. Now, by the way, f of x does have, since it's plus 0 here, it does have a horizontal asymptote at y equals 0. I'm going to go ahead and put that in there. So I am not going to cross this. It's not happening. And I might actually want to put another point in here because this is going to become something to the other guy. So let's plug some numbers in. If I plug in a 0, I get a 2 back. If I plug a 1 in, I get a 6 because 3 to the first is 3 times 2 is 6. If I plug a 2 in, I get an 18. Kind of interesting there, how that worked. But it is what it is. And I'm probably going to have to do a little bit more because this one's kind of funny looking. But anyway, so I graph this guy. It contains 0, 2. It contains 1, 6. And then it's got this 0.218, which is just off the charts here. And this is f of x. All right, looks something like that. Now I talk about its inverse. Things get swapped. So 0, 2 becomes 2, 0. 1, 6 becomes 6, 1. And this thing becomes 18, 2. We might be all right. Now, the horizontal asymptote, which is at y equals 0, becomes a vertical asymptote at x equals 0. And you cannot cross. Let's do a little Gandalf here with his little staff. You shall not pass. You can't cross that thing. Gandalf, Lord of the Rings, yeah, I'm a nerd. But anyways, we contain 2, 0, and then we contain 6, 1. Now, logarithms look like R's. That's what logarithms look like. They look like R's. And that's the graph of a logarithm. Now, something that I didn't put in your notes that I wish I would have, so I'm just going to add it in real quick, is the line of symmetry for all inverses. Anybody remember what it is? It's y equals x. These two lines have symmetry about y equals x. It's the reflection. All right, so let's go back and finish out the little things on here. We have domain and range. The domain of the blue function f of x here was negative infinity to infinity. Its range was 0 to infinity. And watch what happens when we swap around. These two have to swap, okay? Sorry, I drew that arrow in the wrong spot. Those two have to swap. Because if we look at the range of the logarithm, it rises from negative infinity to positive infinity. And then we look at our range and domain swapping. This guy cannot move past the 0 to the left, so it's 0 to infinity. All right, there's one of them. Here's some mom functions. The next time I give a graphing quiz, I'm going to have to include these guys. You have f of x equals a times b to the x. If you made a small table, this would make sense. If you feed this thing a 0, you get a times b to the 0, which is just a times 1. So we always contain 0a. And if you feed this thing a 1, you'd have a b to the first, which is just ab. And these are mom functions. They give you an idea of what these things generally look like. So we're going to contain some point 0a. I'm just going to call here. It has to be labeled because we don't really have an index for A. And you have to contain some point 1AB. You have a horizontal asymptote by default at y equals 0, the line you shall not cross with an exponential. And this is the mom function for all exponentials. Domain is negative infinity to infinity. Default range is 0 to infinity. Logarithms swap some things around. They contain the points b, comma 1. Weird, huh? So let me explain that. If I feed log base b of b, it says what power of b is equal to b? And the answer to that is 1. What a weird thing. Now, something else they contain, and I probably should have put it first, so let me put b1 in the second place, is they contain 1, comma 0. So if you take a logarithm, base b, and you feed it a 1, it says what power of b is equal to 1? And the answer to that is b to the 0, because anything to the 0 is 1. All right, so here's the mom for all logarithms. We contain 1, 0, and then we contain some other point b1, which I'll have to label because I don't have a grid that's done in the letters. And remember, they are inverses, so they're going to look a little bit different. Instead of having that horizontal asymptote, we have that vertical asymptote. It's by default at x equals 0. Domain and range have swapped around. Falls forever, rises forever. And the domain here would be from 0 to infinity. And there you go. 2 new mom functions, basically. All right, graph each function, identify the domain and the range, list any intercepts or asymptotes, and describe the end behavior. And we're only going to do example A here, just to save a little time. This is ln of x, whose base is e. And logarithms, since it's a log, we contain, go back and look at your points here, 1, 0, and b1. So when I do my grid, I am going to contain 1, 0. There have been no shifts. I don't see anything telling me to shift left or right. So by default, I have a vertical asymptote at x equals 0. And let's just do our little table here. We have x, and then we're plugging into natural log of e to the x. I feed it a 1, I get a 0 back because I know it contains that. Now I'm going to feed it the base, and the base is e. So I'm doing natural log of e to the e, which is 1. You know, I know some of y'all won't memorize things. God bless you. You need to be memorizing. Memorization is the foundation of learning. But you get a 1 back. Now, e is a funny number. It's roughly 2.72. So we've got 1, 2, and almost 3. And I did not plot 1, 0 right, did I? That's 1, 0. I'm going to go out almost 3, and then I'm going to rise 1 place. I'm going to draw my logarithm. Even Milbrath, after doing this for so many years, I still sometimes swap x and y. I don't think there's a person alive who doesn't. But there is that one. It did say list any intercepts. You know, you got your x-intercept right there. It's at 1, 0. The asymptotes, x equals 0. Domain is going to be 0 to infinity. The range is going to be negative infinity to infinity. I already got the vertical asymptote. Talk about end behavior. That's something that a lot of kids don't like. But as x runs left to negative infinity, as it just runs left, okay, y falls to negative infinity. And I actually shouldn't say negative infinity. I should technically be saying 0. As x approaches 0, y falls to negative infinity. And as x approaches positive infinity, y is rising to infinity. All right, moving forward. I know I'm... All right, so I actually scratched what I was doing earlier. And the issue with these is going to be tables. I think a lot of you will get your shifts right, but it's the tables that are hard. This is left 3. The left 3 is a big deal because this represents to a logarithm the vertical asymptote, which we cannot cross. Down 4 really doesn't mean anything to a logarithm. It's going to pass through that thing because logarithms don't have horizontal asymptotes. Also, by looking at this thing, I can tell you that the domain is going to be -3 to infinity. Pay attention to those two. And the range for all logarithms is -3 to infinity. That's the easy stuff. That's the really easy stuff. The hard part is making a table. And it's so difficult that I'm actually going to type it out so I can make sure you can read it. There's a couple things that's always easy to do. It's always easy to take a log of base b of b because it always equals 1. And it's always easy to take a log of any base whose argument is 1 because it's always 0. It's always 0. Every single time. That's what happens. So when I talk about a table for a logarithm, and I'll explain why these numbers work, I'll work them out with you. The first thing I want to do is I want this x plus 3 equal 1. And that tells me that a good x value is -2 to feed this thing. The next thing I want to do is I want this x plus 3 to equal 1. Sorry. I did that one. My bad. Somewhere else. The base. I want x plus 3 to equal the base of 2. And that's x equals -1. So these are my 2 points. You'll notice they're not directly related to the shift, but it's in there somewhere. I've tried teaching this with shifts in the past. So let's plug the -2 in. I would have log base 2 of -2 plus 3 and then -4. This is going to give me log base 2 of 1 and then -4. Now log base 2 of 1 says what power of 2 is 1? 2 to what power is 1? The answer to that is 0. And then I have 0 minus 4, which is -4. This is the hard part, man. You got to have a good knowledge of logarithms. That's why I've been trying to get you all to read them. The next thing we do is plug in a -1. I'd have log base 2 of -1 plus 3 and then -4. This gives me log base 2 of 2 and then -4. And log base 2 of 2 says 2 to what power is equal to 2? And the answer to that is 1. So I get 1 minus 4, which is -3. These kind of stink, don't they? They kind of do. Anywho, back to fall 4, back 1, fall 3. And then just come in from up high on the right and flat line on that asymptote. And I know those are rough. I know they're rough. I've done this for years, and I know they're rough. All right, the last slide in your notes is just about writing inverses. That's all it's about. We've got pretty good skill at this so far. Some of you, well, I say about 50% of you do, which is well above average. State of Tennessee, no more than 20% of all kids can actually write an inverse. So we're going to swap X and Y. And that's a true stat. I mean, I see the data from the entire state every single year. We're going to play the isolation game. So if you can write an inverse, you're better than most of the kids in the state of Tennessee. And we have isolated the base. So now we're going to do the whole log is bay idea. Because if you have an exponential, convert it into a logarithm. This is my base, this is my exponent, and this is my argument. So log base 10, argument x minus 4 is equal to y minus 1. And again, the steps from the very first slide were swap x and y, then resolve for y. So we're just going to add 1 to both sides. Log base 10 of x minus 4, and then add 1 is my inverse of f of x. Here we have a logarithm, and the ultimate goal is going to be to take that logarithm and make it look like an exponential. That's our ultimate goal here. So we get the g out on this one. We've encountered an x, it's a y. We're going to play the isolation game. We're going to add 3 to both sides. That's not 3x, quit being that kid. It's x plus 3. I don't understand what's wrong with you. We've been modeling this behavior for years with you. Equals log base 7 of x plus 5. Base argument, which means this guy is the exponent. 7 to the x plus 3 must equal y plus 5. Continue isolation. Subtract 5 from both sides. And there is your inverse of g of x. And the last thing here in this set of notes is your you try, and please try that. All right, there's a lot going on in that one. It is a great recap of what's going on. And sometimes finding an inverse is easier than actually graphing the function itself. It really is.